We'll get started. So I actually don't know how to say your name.
My name or my first name?
Dennis?
Dennis. Denis.
Denis Burgarella.
Burgarella.
Burgarella, okay.
Well, it depends which language you want to use.
Okay. So we have Denis talking to you today. He's going to talk to you a couple of sessions on CIGALE, which is about fitting of galaxies with different models. So
exactly. Okay, so welcome here. Yeah, that's something I will have an introduction right now, and Patrice over there will have a hands-on session on Thursday, I think, when you can apply what you will see here. And I'm not sure exactly what is your level about ACD fitting, etc. So I start at very low level and maybe try to increase later. So this is a summary of CIGALE and what it does, what it doesn't. So basically, it's about galaxies and only galaxies. You can do smaller stellar population like global clusters, but you need specific models. And you can derive several types of parameters about the stellar population, about redshift, if you want to, about dust, about AGN, which is somewhere as well. And everything is related to comparing models to data. The basis of this model is the energy budget or balance, which means that you have data in the UV coming from stellar emission, which can be processed by dust grain and re-emitted in far infrared. So we try to keep this as a balance between what is absorbed and what is re-emitted. Actually, some people tell that some infrared emission cannot be estimated from this energy budget. And we could have something to force some infrared emission without any identified UV source. But it's very specific. And finally, one of the specifics of CIGALE is that it's very fast. And we'll see that at the end. So you can use it for very large amounts of data, photometric, spectroscopic, etc. I will try to have the cosmic dawn image whenever it's related or specifically related to what we are doing here. So let me start by definition. We have spectral energy distribution. That's distribution of energy of an object, more specifically a galaxy here, over wavelengths or frequency. Even though ACD doesn't mean it's only photometric, I try to have another one, which is spectrophotometric energy distribution, which is meant to explain that I don't only use photometry, but also spectroscopy. And you can combine the two information. By spectroscopy, we have two meanings. You can use line indices, absorption, emission, or you can use spectra. And finally, by fitting. Fitting is a statistical procedure that is meant to characterize the objects that you have here. And by comparing these observations to models, you can derive physical parameters that try to explain what is the nature of this object. Of course, it depends on the uncertainties, the type of models, and many other parameters. CIGALE is quite a complex machinery. So you have different components that you can put into the model. You have, of course, stars at the beginning, but you will have gas that is related to the nebula emission, dust, and you can also have an AGN that is inside the galaxy. And you will combine everything using some kind of slider to get some model. Obviously, before doing the ACD fitting, you don't know which model you need. So you will have a range of physical input parameters that allows to create many models. Normally, we get good match from, well, if you don't have any prior information, if you use 100 or 200 million models, up to 1 million models. If you use 100 models, that won't work. So we have gas, we have stars, we have AGN, and we have dust. All of this is not mandatory. Of course, stars is very useful because it provides the UV emissions that will be used for the dust emission. AGN and gas or nebula emission can be optional. It depends on what is your objective and what you want to do. And so from the observation, that's in French, so you can practice a bit. I just noticed it. You have different information that you can use to derive the physical parameters of the galaxy at the end. And depending on what you put in these different branches, you might get something different. So it's not a single process. I mean, you can do just a single process. You put many parameters, and you look at what you have at the end. But usually, you don't get a good answer. You need to iterate, because the range of parameters that you have, the type of stars or the dust temperature, will need to be optimized depending on what type of information you have. So you might need to run this several times, and that's why the speed is very important. So we have here one SED, the flux in milligensky, which is a normal unit for CIGALE wavelengths. And this one is very well sampled, SED, as you can see, from the UV, optical, near-infrared, mid-infrared, and far-infrared. So the objective is to compare this type of observed data to observations. To models. And as you can see, well, this model doesn't fit the data. Specifically, we need to do something better. So the process will compare several of these models to the data. You can have several samples of galaxies, 1,000, 10,000, 100,000, and compare everything. And the objective is to have a comparison between all of this. Some can be detections, others can be upper limits, depending on the type of information. For instance, usually, if you have stellar emission which is strong, we know that infrared detection is not very good, and so we have upper limits. If you have the Lyman break here, you will have upper limits below. So you need to have all this information. Well, you can have this information, but you need to understand really what type of data you have to model this galaxy. And finally, by fitting all of this, the modal flux and the observation, you get the best model. One point is that this is meant to compare observations to data. However, we might have some need to just model spectroscopy, photometric data without any observed fluxes. So this is also doable. You just provide the parameter you want to get, the redshift, the type of stars, the stellar population, etc., and you will get the models that you can use to make predictions or to prepare observation runs, for instance. So this is the final objective. And from this, you have the best fitting model, single one, no uncertainties. You will have a range of models that are consistent with the data within some of the information you want to get. And for instance, here you have the star formation rate, SFR, here, and this is the probability or some related to the probability. And you see that the PDF, the probability distribution function, peaks at point, let's say 45, but you have other peaks here. So the best one will be this one. Statistically, however, it's not exactly this one. It's something which is around here. So you have a best value. You have a mean on an average value and some uncertainty, which is related to the probability distribution function for the SFR, but for any other parameter. So how do we do that? As I told before, we have several components, young stars in H2 region or star-forming regions. You might have old, young and old stars as well. You combine the two of them. Gas will produce the nebular continuum and the nebula emission. Dust will absorb the stellar emission and maybe some part of the AGN emission and will emit infrared. So a good model for a galaxy will include all of this. If you forget something, which is actually in the galaxy, your model will be wrong and the result will be questionable. So stars emit from UV to near infrared approximately. These are the high energy photons ionized the gas and re-emit these photons through emission lines plus some continuum. The dust clouds get the photons and emit in infrared. And you can have other components that emit in X-ray, radio, etc. And well, I won't cover this here, but you have different type of modules, as you will see, that allow to capture all these type of emissions. So let's start from the beginning. Well, of course, this is transparent for you. You assume some parameters at the beginning, and you get the result. So here you have two types of stars, young and old, and this is just the stellar emission from these two types of stars. Of course, you rarely expect to have only a single stellar population, which is born at the same time, so you need to assume something more. Well, I forgot, and yeah. So you need to assume the initial mass function. So you have different options. All of them are not inside. It depends on what is provided by the SSPs. And you can follow the evolution of population of stars with the same initial metallicity, created at the same time, and following the same F. And the one we can use are, well, we can use several into CIGALE, which is most useful right now is Burgarella Shadow 2003, but you can use other one like BPAS, the updated version of Burgarella Shadow 2009, I don't remember, 9, with binaries, etc. So you have different types of SSPs that you can give as input to CIGALE to estimate the stellar emission. And all of this is normalized to one solar mass. So that means that at the end, you have, with different ages, this type of stellar emission. So again, from BC03 here, from younger to older stars, which need to be combined to reproduce what you expect or what you will have in your galaxy. Because you don't have a direct peak in star formation, you will need some star formation as a function of time. And this is a star formation history. This one is called a delayed one. That's one of the examples. The most general one that you can use, assuming an analytic SFH like this one, is something like this. So it increases very sharply at the beginning of the lifetime of the galaxy, then a slow going down, and then you might have a peak at the end because you have a rest and burst at some point. So combining the previous information with the star formation history, you can do something. And here you have the stellar emission from the young stars. Young means younger than 10 megayear. You can change these parameters, but it's what we usually use. And the older stars, of course, young stars are more UV than infrared, than old stars, and vice versa here. And you have these two stellar populations. Why do we have two types of stellar populations? It can be important, for instance, if you assume that you have one single population inside molecular clouds and one outside, depending on the type of dust attenuation law that you assume. So you won't have the same amount of dust attenuation for the two stellar populations. When combining the two of them, you get the yellow one, which is here, which is the one you assume, the emission you assume coming from the stars in the galaxy. this part here, below the Lyman continuum, the Lyman break, sorry, is the Lyman continuum, as this information is used to estimate what is the nebula emission, the continuum that you can see here, and the line emission. And we use cloudy modeling, that's a paper by Patrice here, very recently, with different types of parameters, like the excitations, the metallicity, the density, electric density, etc. So that allows you to estimate what is the nebula emission depending on the type of parameters that you want. You can also assume some escape fraction and change it inside the models. Then, once you have this, you move to the dust attenuation. So this is the model without the Lyman continuum. We assume a dust attenuation law. So this one can be changed. You have different one with different baseline. If you assume a Galaxie baseline, which is this one here, you can have different slopes. So you can change the slope of the dust attenuation law, and you can add a bump if you want to. And well, this is from a paper where they found out that there might be an evolution with redshift, which is still to be confirmed. But still, you can change this, and it produces different results. I think you don't see very well, but if you have stars and dust in red mixed, this part here is the stellar emission, unattenuated, and having this type of geometry implies some type of dust attenuation law, and you see that you have only a small dust attenuation. On the other hand, if you have the stars here and a screen in front of the stars, you will have a very different dust attenuation law, and that changes a lot. So this is something very important when you want to model your galaxies. Of course, if you have dust, or you assume you have dust inside, and you need to be very careful at allowing a good range of slope, bump, and using different one. So we have different types of dust attenuation law, and you need to select one at the beginning. So this is what you get for this just illustration, the unattenuated and the attenuation, which is here. So when you do that, you have some energy here, which is absorbed by dust grains, and re-emitted here in mid and far infrared. This is what I called energy balance at the beginning. This and this energy are the same in terms of energy, and you need to have all this integration here, which is used to assume what type of, no, not what type, what is the amount of infrared luminosity that you will get. Of course, the shape itself is something different. It's just the integral of the dust emission, which is coming from here. So combining everything, the stellar emission, the nebula emission, the dust emission, you get this final luminosity here. This is in watt per nanometer as a function of wavelengths. And this is one of the models that you will use to compare to the data. This is in luminosity. We convert this to flux because this is at 10 parsec in absolute value. Because we compare these models to the observations. And then, once we have this, we need to understand exactly what is inside here, what are the assumptions. So in the UV, you have young stars, which provide you or can provide you with a direct estimate of the star formation rate. If you go until the optical and infrared, you have evolved stars. This is a characteristic of a tracer of the stellar mass. If you have data here that allows to constraints, for instance, the pHs, the metallicity, or the edge infraction. So this is quite closely linked. In the far infrared, you have the hot dust. That can be the hidden star formation that you get from here, preprocessed here. Also the RGN, depending on the temperature of the dust emission. And in the submillimeter and millimeter, cold dust, which is important for those mass. This is, of course, at redshift 0. If you're working at redshift 2, 5, 10, everything changes. So if we use this code, CIGALE, we are doing this type of energy balance. And the main parameters, so you have stars emitting in UV that you get from in your telescope, whatever the telescope. Then you assume that you have some dust clouds. And the dust attenuation here produces some infrared emission through ray emission in far infrared. And from a single spectrum here, assuming different dust attenuation, you see that the infrared emission increases a lot, the dust attenuation decreases, and this is completely consistent with what you expect when you have the energy balance. As I mentioned before, we might have in some cases to assume that there is something, well, we don't see the UV stellar population because it's deeply embedded into dust, but so you might have a small amount of infrared emission which is outside the energy balance. This is a very specific option, but it's possible. So, in the process, what do you do? So you have your flux densities. You have different types of model for a given survey. And you will first estimate the normalization, which is related to the mass of the galaxy, and compare the data to the models using a traditional chi-square. And the normalization enters here because you need to compare the model to the observation with some uncertainties. So in this specific case here, you see that you have a very good match here. You have a good chi-square for these three models, which is a good result. However, as you can imagine from this, if by perchance you get some infrared data, you might have something which tells you a different story. The green one here provide a good chi-square, while this one and this one provide a bad chi-square. So that's meant to show that whenever you do some LCD fitting, of course, you might have data here coming from one single telescope in UV optical or something else. But if you want to have a complete view of your LCD, you will get better parameters at the end because you will combine all the information that is available. This is valid for infrared, but we will see an example also if you have X-ray values, for instance, or radio. So the more information you have, the best the model will be, the better. And so you get this at the end with a good match for everything, even if you have upper limits and uncertainties here. And this is not only, let's say, an example that is not valid. This was proven to be very useful at some point. So, for instance, when we got the first photometric data from JWST with NIRSpec here, we, and you probably saw many papers assuming that you have galaxies at all redshifts because the fit was very good in the NIRSpec range. And, well, of course, this is logical, assuming the chi-square is valid estimator of the goodness of fit in this range, you get something. But as I mentioned before, we have also some information, or we could have some information in another wavelength range, which is very useful. So here we had Spitzer, and I think Herschel, and we have also Scuba-2 data. And if you assume only the NIRSpec data, you see all the models are very consistent, and you can have different redshifts at the end, 5, 5, and 13, using photometric data, of course. But if you use this information, especially the Scuba 2, you see that the best models would be at different redshifts, well, not too different, one of them, 5.1. And that illustrates the fact that the information that you have in a given wavelength range is crucial. But the one you get in a different one is even more crucial because it will give you a good handle on, for instance, the redshift in this case, and the estimation will be much better. This one and this one are not in agreement with the data using this. And, well, we saw many of them. This one, for instance, we had a galaxy which was supposed to be a 16.4. And the ACD fitting was supposed to provide a redshift around 16.4 with a very nice emission in the priority distribution function. However, depending on what you put in the parameters at the very beginning, you might have another peak that appears at redshift 5.4 here. And that provides you with a different redshifts. And this was assumed at the very beginning. Once we had the spectroscopy, we had the lines. So these galaxies was found to be, well, if it's the same exactly, at redshift approximately 5. And we find a very good match with the emission lines that confirm that galaxy is not at redshift 16, but at redshift approximately 5. This is due to the fact that here, when you have only the photometric data, you can see the slope here. It's about this. But this needs to account for the strength of the line emission. This is H beta, this is O3, this is H alpha. And that changes the slope a lot and provides a wrong redshift if you don't assume a good range of parameters. If you, by seeing this, if you just assume that you have galaxy with a low dust attenuation, you will miss the peak here at redshift 5. So you need to be very careful about it. So, well, everything I mentioned here is valid for all the ACD fitting code, or most of them. This one, CIGALE, is a code investigating galactic emission or galaxy emission, depending on the version. And we design it to be very modular. For those who don't know, this is a CIGALE, a cicada, because we have a lot of them in Marseille. Yeah, I know. So we have many modules, starting from nothing. We assume star formation histories. We assume stellar emissions. From this, we have the nebula continuum and nebula lines. Then the dust attenuation takes part of the emissions that you have before, including line, by the way, and is re-emitted here in the infrared. You can have also an AGN, which has the same problem with energy balance. And finally, once you have all your models here, you redshift everything, and you add the AGM absorption to compare with data. And the said ACD object at the end is what you will compare to the observations. So if I want to detail all of this, so you assume a star formation history, and you combine with a single stellar population spectra. The dust attenuation law, as told you before, is crucial because it will constrain a lot of things through the energy balance. So everything absorbed here is fine here. And you can add also modules, in particular the dust emission, the AGN if you have one, and the gas emission. And finally, you will get a large range of models, 10 to the 6 to 10 to the 9 galaxy models that you have here with all the components that are coming from your assumptions here. This is from Groves et al. And all these models here are compared to your data. So this is a lot of time, depending on how many models and how many data you have. We took care in CIGALE to be very fast with this one is written in Python, and we parallelize everything, taking care of all the memory is managed, putting that in caches, and that allows to get a very fast run for CIGALE. So we compare every single observation, or SED, to all the models. So each time we have good fit, bad fit for each of them, and this is quantified. Once you have done this, you will get a probability distribution function like we saw before. And this will give you, well, the best one, which is this one here, then a mean or average or anything, and an uncertainty coming from the distribution that we assume Gaussian in this case. And this is valid for any parameters, redshift, even though when you do a physical analysis, you assume that you know the redshift, or at least some good estimate, but mainly all the other ones. CIGALE is not defined or designed to estimate redshift. It can be used as a parameter like any other ones, but the best use would be to estimate first the redshift using another code. Probably the one that are specific to estimate redshift, and then you derive the physical parameter in 2 different steps. You can mix the 2 of them, but also because here you need a lot of redshift to get the good one, it's better to estimate first the redshift and then the physical parameters. Just a bit of history. The first one was written in Fortran by myself a few years ago. Then the second version, still in Fortran, by Noel et al. And the change between this one was to use mainly the UV and optical models, and to compare to infrared data, so we just use infrared luminosities. Then we move to a more physically oriented models, because we had still galaxies, but spitzer, and selection of the different modules via an input file that tells you which parameter you want to use for which modules. The next step was in 2012 by Yannick Rowley in LAM, and it made a lot of changes. First, this version 1 is in Python, and there was a structure of the code that allows to get all the different emissions and assumptions into different modules. But you had a backbone, which is a structure, and a database, which is the same. Which means that for scientists who want to add a simple module, you don't have to change everything or enter into a single code. You just write a short, or depending on the complexity of your module, a short code, which is usually very specific. You put it inside the directory where you have all the science modules, and that's it. If you took care of having the good interface, it's included into CIGALE. So it's very fast, and we can adapt. If you have new SSP, new dust emission, new dust saturation, whatever, you can do that. So this one was the first Python version. Then we moved to a parallelized version for the spin and for a model. This was done by Médéric Bolquin in Nice in 2019. And we also include lines. There were lines here, but very simple, just to show that we have some. It was mostly aesthetic. But here we could start to have new ones. And now, 20 years after the first one, I implemented the spectroscopic data into CIGALE to have the possibility to add spectra and to fit spectra, well, actually spectra and photometry. So we have a lot of different modules. Not a lot of them are useful, but well, it's historical. We keep them. And we will see that we add new ones. The star formation history, SFH, is very important. So we have different ones. with different specificity. You can even have input coming from files. If you use modeling from hydrodynamic models, for instance, you have different SFH, and you can provide them as input into CIGALE. The good point for this is that because it's modeling at the very beginning, you will be able to compare what you get with what the model gives you in the modeling of galaxy evolution. Single stellar population, so Buzzer and Charlot, Marston, BPAS, and this is updated every time we have a new one. You will see that. Nebula emission, so Patrice can explain you everything about it. Dust attenuation, we have this one which is coming from shower rainfall. So you have two power laws with different indices. And this is specifically because you have a young and old stellar population. And we modify this one, called starburst, because it's from Calzetti in the UV and Leiserer et al., so quite old papers, in the extreme UV. Dust emission, KZ 2012. That's a power law in the mid-infrared. And then traditional all types of modified black bodies, optically thin, optically thick, depending on what you get. Dell, Drennan-Lee updated, and Themis, which is from a library coming from Paris. AGN emission, we started with Fritz 2006, and then Skirter is the updated one, 2016, with different components coming from the disk. You can have polar dust, you have the torus as well, and so you can combine this with all of them. X-ray from the AGNs, but also from very energetic stars. Radio, which is very simple, and then redshifting and intergalactic medium. So the first version that I wrote, well, it was not like this, but almost. So it was something that was very simple and just meant to compare GALEX data to IRAS data. That was the very beginning. And at this time, we had, of course, only photometric data. And because of GALEX, we have these two main bands that were primordial for us to derive parameters. Then Stefan Noll modified it, still in Fortran, by having these different modules. And that allowed us to be more specific depending on the type of galaxies that we looked at. Before, it was very, very simple. We move to the next one, the Python code by Médéric Boyker here, and with a lot of input from Yannick Relly here. And this is mainly what we have right now. We have all the important information, the flux, filters, model property, model, something I can read, the Bayesian estimate, and the best fit. And this is done using different modules for SFH, stellar population, nebula emission, etc., etc. And we get the parallelized analysis of all of this, one object per core, which is something we get. And finally, we can combine everything. This is flux and this is wavelengths for all of them. And you can, at the end, get the contribution for every single component that you have assumed here. And so you can see what is the contribution coming from, I don't know, the AGN, what is the absorption from dust, et cetera, et cetera. So this was an important step. It's probably the most important step because it made CIGALE becoming a very fast code, keeping all the modularity of the physics that is inside CIGALE. And, well, again, that's the same thing I mentioned before. You can estimate redshifts with CIGALE, but again, it's not the main purpose. For other codes, you can ask Rosa here, and there are many ones that are more specific. They provide redshifts with better answers and faster. But once you have a redshift, you can come to CIGALE. Well, if you want, you can start before. Some new things that will appear appeared recently. The AGN emission, right now we have these two Fritz and Skirter models, but we have new development, which is very important, because we have more and more data in spectroscopy coming, for instance, from NIRSpec, and we need to model the lines themselves for AGN. And this is something that is done right now. We are close to getting this emission that will be included into CIGALE, and you will be able to model the AGN emission in addition to the other one. That means that there will be more parameters to control because these lines are very important, the width, etc. And the physics, of course, is crucial here and not related to what we have above. So this module is very important and means a lot because we have a complete coverage of most of the physical processes inside the galaxy. So right now, this is what we have. This was developed by Wang Yang when he spent some time in Marseille. And basically, you have the same things than before, the break, the UV optical infrared, etc., for different galaxies. But here you can have the AGN emission that was Fritz, I guess, here, to 2006. But also, you can add some input from the X-ray. Well, you have a gap here, which is now being corrected. But you can control the SED from the X-ray to the far infrared and even the radio. So if you have a good match for an SED over such a wide wavelength range, you are very likely to get a good result at the end, depending on your uncertainties. So this was very important, and we had a specific paper on this. At the beginning, this CIGALE X was a different version because we required some different processes. But now it's fully integrated into the public version of CIGALE 2025. So I mentioned that we have different star formation histories. And very recently, we had the stochastic SFH. Well, you will hear Christian on Thursday, I think. We know that this is the bursty galaxies and well, the proportion. This is redshift, and here that's redshift again, and a ratio of star formation rates for young and old stars. So we, or Christian and other people, found that you have an increase of this burstiness at higher redshift. So because we are looking at cosmic dawn now, we want to check if this burstiness is something we find using different types of model, but especially model with stochasticity. For this, I use this framework, Takela, Forbes, and Kepler, where you have different physical processes. Well, I need to press. So you have the gas, the atomic gas making molecular gas. Then, of course, you have the reverse one. This gas can make stars, and the return fraction will go back to the first reservoir. And all of this is regulated, controlled by some inflow from the intergalactic medium. So this approach here provides a physical explanation on how SFR vary over time through different time scale, and that's what is called regulation. So that's a regulator. So the time scale over which stochastic gas inflow here, and what is the correlation. The mass loss or equilibrium time scale on which gas is consumed and removed from the reservoir. And finally, the average Jane molecular cloud lifetime time scales. So you combine all of this to model the star formation history in something which is quite stochastic depending on the type of parameters that you have. So if we look this, well, actually, I mentioned Takela, but it's more the paper by chaotic IRs that I used. And to assess what is the level of burstiness or stochasticity in a galaxy for the past star formation, of course, as a function of time, we move to the Fourier space and use the PSD, the power spectral density of galaxy over time. So this is the power spectral density from Ayer et al. So you have here the PSD, and here's the time scale. And you have this, what is called the extending regulator model, where you have different processes here, the gas inflow and cycling, the dynamical process, and the general clouds. And all of this is combined over time to produce the star formation story. This is in the Fourier space. If we move to the time space, so that's the autocovariant function, you have here, well, it's more or less reverse, the dynamical process, gas inflow and cycling, which is here, and finally, the total extending regulator models. So depending on the type of processes that you assume in these three ranges, you have different things. And the Gaussian process allows to draw different random process that will suggest that you have different types of star formation story. So this is a log of the star formation rate as a function of time. And you have different realization through the Gaussian process. This one or this one are different burstiness. And of course, because you have a different star formation story, you will get different SCDs here. So assuming you have a very good handle on your data, from the spectroscopy, from the photometry or the spectroscopy, you can have a very good physical handle on the star formation story. Of course, like we saw before, if you just have photometry, well, that might be a bit difficult, but if you have spectroscopy, you have the emission lines, which is even better. And you can try to derive some constraint on the star formation story. So if you want to know more, Christian will be talking on Thursday. So mathematically, we have here the power spectral function here, which is related to different types of parameters, but basically it controls the stochasticity. And in this extended regulator model, we have the inflow that we saw before, the equilibrium between the different mass of gas, and the dynamical or the giant particle cloud contributions. And what we do is that we combine these two ones into a single one, which is related to the gas, and this one to the clouds. And finally, the Gaussian process is used to, assuming a baseline, that means you have something which is smooth. It could be, well, I think I write it before, after. It could be a delayed or an exponential in CIGALE, but we can have anything. On top of this, you have the Gaussian process that gives you some stochasticity. And you finally get the SFR, which looks like something like this, depending on what the baseline below is. OK, so that was the first part. So the one that is very important for the cosmic dawn, because we expect, as we saw before, to have more stochasticity at higher redshift. Then another one is still related to cosmic dawn, is population-free models. We know that we will, or maybe we might, we can ask Roberto, population-free galaxies detected probably sooner or later. And this shows you, this is from Scherer et al. I think it was 2000. So you have a galaxy here, the helium-2 emission, the main helium line, and I think this is helium as well, helium-1. So you have this type of emission. And at redshift, this is West frame, of course. At redshift 9, you're exactly in the range corresponding to NIRSpec or NIRCAM. And so we can say that if we detect this version of helium-2, that means that you could have a population-free. Of course, it's much more complex than that, and you can have different processes that produce this helium-2, everything energetic. But that's not the point here. What I want to stress here, this is the same thing, assuming a salpeter EMF over this range. and this is on the zero-age main sequence, 2 megayear and 4 megayear after. You see that these helium-2 lines disappear very fast because they are due to very massive stars, 07 or like this, and the lifetime is just a few million years. So if you wait too long, and too long is not very long, you won't get these helium-2 lines, and you will have something where you might have even production of oxygen. So the window to detect this population free is very narrow, just a few megayears after the formation of this population. And that might explain why it's so difficult to detect these galaxies at the moment. Again, so here that's from Fujimoto et al. Well, that's one of the papers mentioned before with candidates. This is an ultra-faint 10⁵ population-free candidate at redshift 6.4. And this is what you get assuming population-free, and this is assuming a metal-rich galaxy. And you can see mainly the difference. Well, which are underlined here by these pink bands. Well, first, outside the bands, you have many other lines that are metallic lines that you don't expect to get in this type of population-free galaxy. Then, for instance, no oxygen-free here. That's the oxygen doublet here. Next one is a Balmer jump. If we expect a very young population-free galaxy or stellar population, you will have a larger Balmer jump that can be used. It's not written here, but the UV slope as well could be very important. And H alpha, especially the equivalent width, would be very high here. So you can have some measurements that allow you to make the difference between the two types of populations. The problem is that it's not obvious all the time, given the uncertainties, the errors, that you get the best estimate for these parameters. And that's why we have still candidate and no confirmed population-free, as far as I know. So in CIGALE, we have implemented the Yggdrasil model. I'm not sure how to pronounce it. That comes from Sweden, Zachrisson. And we have two main parameters. First, the IMF of population-free, not two, is not well known. So we have several assumptions inside. Population-free 1 galaxies that assume Scherer et al., or Scherer only, stellar SSP with a polar IMF with this slope, but very wide range of stellar mass for the stars. So this is a lifetime which is very short. Then the 3.2 is about the same, but with a much lower characteristic mass of 10 solar mass up to HD cooling. And you have some feedback via the Lyman-Werner radiation over this one. And for this one, the models, Yggdrasil use Reiter et al. 1020 with a log normal AMF and this type of characteristic mass with this dispersion. But the wing can extend by 4. And finally, the third one use the same Krupa AMFs that is used for the population 2 and 1, but the contribution is computed as an input to the photoionization cloudy on this one with a wider emission. So that's the first choice that you have to make when you want to use Yggdrasil. The second one is this coverage fraction, and the covering factor F curve here regulates the relative contribution from the nebula emission to the final SED that we saw at the very beginning. So this is quite an important parameter because it controls the strength of the nebula emission in the line. And it also controls the escape fraction, which is just the opposite as is written here. And because of the Yggdrasil, we have 3 values only here that allows to explore what are the differences that you get assuming a different F curve. So that's the 2 main parameters that you have. That's not a lot, and we need to be careful about it. And once you have these population-free models, you use the save flux option into CIGALE, which is to produce model, spectra, or photometry. And you can create such diagrams for paper proposal, for instance. So this one was from Zachrison et al. In 2011, so it's a bit old. Assuming we have these 3 ones, the other ones are not inside Yggdrasil, but we have a lot of them outside Yggdrasil. And you can compare here the color in these 2 bands as a function of age. And you see that the population-free region, if we trust Zachrison, would be in this range where you have mainly population-free, 1, which are up to here, so very young, 3, 2, and Krupa. So if you get galaxies with this color, well, it could be population 1 with low metallicity, no, solar metallicity, but you have a better chance to get at redshift 8 some population 3. If you move to MIRI, assuming it's still working very well, you have the same type of diagnostic here with these 3 population 3 in this bottom region, while the other ones are above. If you are lucky and you get this data and this data, you can, of course, combine the 2 of them and try to have some population-free candidate in your sample, or you can also make predictions if you want to have a JWST or whatever proposal. Because you have the line emission, you can also predict some little lines like O3, 88 microns or something like this that could be combined with what you have and give more strength to what you will get. Especially because you expect this O3, 88 micron in system emitter to be very strong for very young star population at high redshift. So different ways to use CIGALE. So you have the integrated what is called PDF analysis. So you will see that on Thursday. And this allows you to observe, to analyze observed galaxies and to infer physical parameters by comparing the model to the data. And you have the save fluxes method that allows to generate mode catalog corresponding to the various physical parameters that you want to select, and to produce mock catalog, prediction, etc. And you can also use CIGALE programmatically to generate spectra on demand and templates, libraries, etc. So you have different ways to use this type of code, well, CIGALE and probably the other ones, for different objectives, analyzing data or making prediction or mock catalog. So you will see that more details, but basically you have this command to generate this file where you edit and add the catalog file names and the different types of models you want. From a module here, then configuration of the generation of the configuration allows you to fill in the parameters. You can check if everything is okay, semantically, and you read it. And after that, you can plot various things if the fit is okay. And finally, for each object here, you will get various parameters, star formation rate, error, that's the same one. No, this is a Bayesian value, and this is the best value. So this is only a single model, so you don't have any uncertainties on this. And using this type of analysis, you can estimate all the physical parameters related to what you gave into CIGALE as input. So age, SFR, attenuation, mass, dust luminosity, attenuated, of course, if it's in infrared. What is the attenuation in some band, far UV, V, whatever. And you can also calculate some specific indices like D4000, the iris thing, the UV slope beta, red frame colors. And you can predict fluxes in any observed band, assuming you have the transmission. And of course, anything you can measure on a specific spectrum, provided you write the corresponding module. If you want to have something which is new, we didn't think about it, you just write a module and it will provide you with this value, because you just throw it inside CIGALE and you will get it. So we are here interested by what happens here. So we get some population of stars and galaxies evolving over time. We can control all of this. And of course, the better the information, the better the result. So if you get spectroscopy, it's better than photometry, assuming spectroscopy is good enough. So what's new into CIGALE? So we have James Webb. James Webb is providing a lot of photons that allows to build spectroscopy on very distant objects. So for instance, we have all these galaxies here. This is a 2D spectroscopy. And we have here the 1D spectroscopy for all of them with the Lyman break sometimes and various lines as well. So H beta or 3 at lower redshift. So we want to analyze all of this. This is very important. And we saw that using only photometry is a good start, but getting spectroscopy is much better. So just a few examples here. This is Maze's galaxy. That was one of the first ones that we get with JWST in our program, CIRS. And you see that we have the spectrum. So the blue region are the uncertainties. Here you are below the Lyman break. So of course, you have just upper limits, these triangles. Here you have a lot of uncertainties, the red part or NIRSpec. And you have the photometric data. Because we want to combine this spectroscopy to photometry to have a better handle on the shape of the continuum, for instance, we can combine or normalize the spectroscopy to the photometry. Well, if you don't want to do it, it's fine. You can just use the spectroscopy. For instance, you don't have any photometry or you don't trust him, or you look at different regions in the galaxy in photometry and spectroscopy. So you can just fit the spectrum. If you want to actually normalize the spectroscopy to photometry, you can do it just by having a single normalization or wavelength-dependent normalization. What we do into CIGALE is that we have different polynomial approach starting from degree 2, 1, 0, and a statistical test will select which one is the best, 2, 1, 0. And we apply this correction. So we don't do it blindly. We first check, assuming the uncertainties that you have on the photometric and on the spectroscopic data, that you can make this correction. If not, we just go back to the simple one, constant normalization. So this was a very crucial step when we wanted to compare photometry and spectroscopy. Then we have the nebula emission here, and we wonder in the CIRS team whether or not it would be the O2 emission. And by comparing the data with the models, we see that really that we seem to find exactly the same position, and the prediction is quite nice as well. So this is probably very likely the O2 emission in this galaxy at redshift 11.4. And you can notice the chi-square, which is quite good. We might also be able to estimate more difficult. So here you have the continuum, and you see an increase that might be consistent with the Balmer break here. We didn't look at it precisely, but we see in different galaxies different Balmer discontinuities that we might analyze, and that would provide some information on the age of the stellar populations that we find in these galaxies. So this is something we can do, of course, because we have the model. We are not restricted to redshift larger than 10, and you see that JWST, or you know that JWST has many, I estimated there are a few 10,000 spectra, NIRSpec spectra in the database from very local galaxies to the highest redshift, or at this time when I made this slide. So we have all of this, and we can analyze all of this to get the physical information on these galaxies. So in this paper, I just introduced the spectroscopic version of CIGALE. And we have in this paper some NIRCam data, NIRSpec data, and also some data coming from the far infrared Scuba 2 and NOEMA. Most of them are only upper limits, so not very useful, but still it allows to discriminate from low redshift dusty galaxies to high redshift plain galaxies without dust or less dust. So this is a full range that we use in the ACD fitting. If we focus on this part here, you see that we follow, so the red dots here dots are the observed photometric flux, and the crosses are the model photometric fluxes. So you see that we see very well the continuum. This is quite, well, relatively low redshift, let's say. But we model quite nicely the continuum of the galaxy over the entire range. And even more, we also get some fit of the lines themselves inside the code without doing anything more than applying the normal process. And this was something that was quite interesting, because by fitting all this data here, you could get some estimate of the line emission, assuming some weights, and you can derive some physical information on various things like the ALMA decrement, if you use H alpha, H beta, the metallicity, etc. So this was quite nice find at the end of the process. You can also use CIGALE in 2D, which means that you will have here the data for every single pixel. So this one was done at the very beginning, so we had only photometry, and which is below. And using CIGALE, we fitted everything. We derive an estimate of all the physical parameters for the galaxies here. We compare that summing up all the pixels and comparing to the integrated one, we get very similar values, which is a good information, which means that we can trust that. And the good point here is that we had the possibility to estimate what is the line emission that we didn't have at this time, and the H alpha contours, which is here. And you can predict various things. This was, I think, the infrared emission, the UV emission. So you can distinguish between different regions inside the galaxy, or different redshifts as well. And we can use that on every single pixel to combine that. And at the end, we got some spectroscopy, and we measured H alpha. And so the prediction is below, and what we measure is a bit outside. So we don't have a direct comparison, but we could do that now. But the point is that you can use pixel by pixel and rebuild the map for anything you want: lines, continuum, mass, attenuation, whatever. So if you want more information on this CIGALE spectroscopy, you can look at the CIGALE website, which is only this, and go to the news. You can download the spectroscopic version of CIGALE. So you have to be careful. The one you will use on Thursday is not compatible with this one. So you will need to have two versions.
I just had a question going back, like here, reduced chi-squares that are reported in each bit. I was just curious what the effective degrees of freedom are in this bit. Like how many free parameters that come out being two in each bit, and like how that is overfitting in this case.
Well, actually the process, well, it's quite a difficult question. The process itself compares one model to one object. So the degree of freedom is 1. You can have different parameters, but when you look at the process itself, you have one signal. So we assume that we have this. If you want to try to use different degrees of freedom because you have different type of data, you need to be very careful because, of course, you have some data that are correlated. If you move to spectroscopy, it's even worse. So that's something that proved to be difficult, and we were not able to use this specifically for this acidity. So we can compare it in some way using this reduced chi-square, which is assuming that we have the number of data used. But it's not very good approach, I would say. I mean, that's what everybody does because we don't have any other way. So if you want, we would need to run the code once, get the result, estimate the degrees of freedom, assuming you have or don't have any correlation between the different data that you have, rerun CIGALE, assuming this one. We tried this, it doesn't change the result at the end, it makes the process very complex. So right now, it works like this. One point related to this is how we handle the fact that we have spectroscopy. So I don't know, for NIRSpec, it's a few hundred points with only a few photometric points. So this, I had a student working on this. He was in statistics, not in astrophysics. And we spent 3 years to work on this. And the conclusion, after doing tests and theory, was that we use the same weight for every. Actually, the spectrum is not a spectrum. It's very small bands over the spectral resolution. And the weight that we have for any single data points here is the same. And even though it's the same, we get good batch of everything. Because, well, if you're far away, you have a very strong level here because you can change a lot. But basically, it works assuming the same weight for every single point, data point that you have, whether it is spectroscopy or photometry. But, well, it's quite a difficult point. And so we worked a lot on this. But finally, at the end, we use the simplest way, and it works quite well. Can be improved, I'm sure. So you can download this version of CIGALE. If you go on the Git, it's called spec, S-P-E-C. And you can find in the documentation of the same website how to use this spectroscopic version of CIGALE. Actually, that's about the same as the normal version. And these are active links that I will send later, but you can look directly on the website. A test sample of galaxies with the output parameters. So you can install this version, run it. Again, not compatible with the one you will use or the public version, and try it for yourself. And you can compare. So basically what I have now in this sample, because of this workshop, is high redshift galaxies. I started at redshift 4, 6, 8, and 11.4. And and another one at 4.5. And one here. I fitted everything, and so you can compare what you get on your fit with what you get here. And of course, well, as you can see, you get a lot of information. These are upper limits. And, well, I don't know why there is one data point here. It's strange. Well, OK, that was the data I got. And so this test sample has also what we call the pcigale.ini file. That is what you put inside the module. So we have one module, which is the star formation history, the stellar populations, the nebula emission, the dust, and, well, redshifting, there is nothing because we know the redshift. And what type of star formation history, so that's the shape of the SFH, the age, if there is a burst, 0, 10%, 20%, what is the age of the burst, What is the type of AMF, Chabrier? Well, I use only two metallicities here. The separation edge between old and young. The ionization parameters, the gas metallicity, the nebula, the escape fraction and the dust fraction, and the line width. And finally, everything related to dust, even something that change the slope of the dust attenuation. And you can also change the type of extension law for the lines. So this is what is provided in the test sample, and you can use it to compare to what you will get. And you can go to the highest redshift, 13, 14, 13.9, 14.2, and you still get some very nice fit over the everything. Here we have NIRCam data, NIRSpec data, MIRI data, 7 micron, here and here. And of course, that adds some more confidence on the fit, being able to fit this one here and here. So what can we derive from this spectrophotometric fitting? Well, everything we had before, plus anything coming from the spectra. So if you want to estimate the dust attenuation, for instance, the Balmer decrement, whichever you use will be very important. If you want to estimate stochasticity, that's very important because the lines are something that you need to have if you want to control very well stochasticity. And well, the first question that we ask ourselves, does it really work to use this line, these lines? So I had a different approach, different from CIGALE, using just line fitting on prism and on the gratings. And I compared the lines. So these are the same objects here. This is each delta E gamma, each beta O3. Here you see the width is larger, so we probably have a line, an AGN, and the UV slope. And you have everything here, well, no UV slope. And we compare the results coming from here, from prism and from gratings for all of these objects. So you have here what we get for each of the lines that are here from the prism. Well, I guess one of them is not prism, it's gratings, but well, I made a mistake. And when you compare all of this, you see that this is a one-to-one line. The color is from UV, well, blue to red. And you see that when you have, this is 3 sigma of the background around nitrogen 2 here. So down to approximately 3 sigma of the background, you get quite nice match here. And the lines that you estimate with the prism or the gratings are in good agreement. When you go below, well, you kind of saturate because you're not able to measure the line because they are too faint, actually. So prism and gratings give you a good estimate down to 3 sigma of the background approximately. Then, using this, we tried to estimate metallicities. And this was used using the line estimated from CIGALE. CIGALE doesn't measure the lines themselves. It compares the spectra to the models, and so that's modeled lines. But we saw that it's in good agreement with what you get. And this is the 12 plus log O over H, so some type of metallicity. And this is this ratio, which is the normalized difference. All these data were on the same object from Nakajima et al., Sanders et al., with or without AGNs. AGNs are these black dots. We have 7 of them, I think. 2 of them are very close. And we compare the metallicities that we derive from CIGALE to the one measured by other papers. This is where the calibration from our lines goes. So above 7.6 approximately in this ratio. When we have this calibration, we get a very good estimate of the metallicity, very consistent with what the other one have. well, the red dots are mainly Nakajima, 2023. When we go below, we start to see, well, I don't know if it's a trend or if you have different ranges here, but you start to see some difference. Well, we don't know exactly because here we have mainly extrapolation from this, so we don't know exactly what is the origin of this difference. That will be studied later on. But in average, for most of the objects, unless you go to very low metallicity, we can estimate metallicity using CIGALE. And if we want to compare this metallicity, so CIGALE provides you with the possibility to use some mock catalog. So you fit the data, you get the best models, you add noise, observed noise on the data, and you refit on the best model. So you know what are the physical parameters in the input, and you see what you get in the output. And here, these are two different parameters that are very difficult to measure usually using this type of approach, CD fitting or spec fitting, the stellar and the gas metallicity. Those two parameters are decoupled into CIGALE. You can measure them separately. So this is what we give as an input. And this is what we get in the output. So you see the correlation coefficient is about 0.7, 0.8. Of course, it's not very accurate. I mean, we are working on the galaxy. The sample was at redshift larger than 6, I think. But we still get a trend, which is very close to 1-to-1, the red one. So we are able to estimate the metallicities, the stellar metallicity, and the gas metallicity on this high redshift sample quite nicely. And if we compare everything, so you have the average here of all the metallicities, and the single one for every single paper and CIGALE in black. This is 1-to-1. You see that there is a very wide range of metallicities. Well, you have most of them here, but you still have others here. And looking at the sliding average, you will see that we are more or less in agreement. So the black line, again, is CIGALE, with some of the metallicity estimated by Nakajima and Sanders. But some of them are in strong disagreement, mainly the one called N2 in Nakajima, involving nitrogen, and this one also involving N2. But these lines are very difficult to estimate because of the spectral resolution. Also, for those at very low metallicities are very faint. So if you forget that because it's very difficult, well, all of them are quite in good agreement over a nice range of metallicity, assuming we work at high redshift, of course. If we move at lower redshift, we'll move to the right. And well, if you wish to find out what kind of resonant application we can do with NIRSpec, I will give a talk here. And this is just a first slide showing that we have a sample of galaxy between redshift 8 to redshift 14. And we have here the dust attenuation in far UV as a function of the redshift. And this is the gas metallicity, in 3 different ranges. And what you can see from this is that all the galaxies which are here at high redshift are mainly low metallicities. And you can find quite a good correlation, so except for some data points. All these down pointing arrows are upper limits. These are true detections. And the other point is that all the higher metallicity ones, that's gas metallicity divided by the solar one, are in this range here, especially the one with detection. So we can get this information on galaxies at all redshifts. It becomes more and more difficult here because we lose the line, but we still have the nebular continuum that can be used with more uncertainties, of course. But it's still possible. And for some of them, we have also the lines coming from MIRI, H alpha, O3, limits on H beta, for instance, at redshift 12 here, that are very useful. So combining NIRSpec, NIRCam, and MIRI data will allow to follow this type of thing up to the highest redshift. So more answers if you're interested. And just, yeah, I forgot this. Just as a comparison, the mean dust attenuation in far UV here was computed from a sample in this redshift range, around 1, 2, in Brett et al. So with different samples, no infrared data, so meaning no dust attenuation or no infrared emission, only detection with MIPS at 24 microns, and detection with MIPS and Herschel infrared. So basically, what that means that you have UV galaxies, maybe normal galaxies, and dusty galaxies. And the attenuation of these three populations are here, here, and here. So all these objects have very low dust attenuation, meaning that the amount of dust inside this galaxy is very low. We have different explanations for this low attenuation. And so the point is that we do observe this. What is the origin of the low attenuation is something still debated. This is the end for the physics, but now I will move to the speed. So in this paper, which is one example, or this one, people say that using Bayesian fitting is very compute-intensive task and requires a lot of time to compare this. And using machine learning is much faster. But I wonder, well, 1 year ago, if these claims are really tested and confirmed, or if it's just something that is assumed without any test. So, well, I compared, because it was handy, with this paper from Laura Bisigello, Euclid et al., with different types of neural network. So convolutional, or this one. No images, only data. Beck et al., without images as well. Newman and Gruen with imaging this type. Hengst, CIGALE, that's the version, the public version 2022. And Lefar, another code that was easy to use. And I estimated different parameters, the fraction of outliers. This was used for ZPhot, photometric redshift only, so no spectroscopy here. This HENMAD, which is an estimator of the quality of the fit. The time for training, which is, of course, for machine learning, which can be quite long for here. There was no information here. And about 20 minutes or 3 days here. And of course, for SC fitting normal one, you have no training at all. The number of objects. So what I tried to do for my sample is to do something which was approximately similar. So around, let's say, 60 to 100,000. The number of models, of course, here none. Here it's about 500,000. And the inference time. So the total time that you want to spend is this for this, except that this is needed only once for a given sample. If you have different samples, you need to do it again and again. So the inference time is 15 minutes, 1 minute, I don't know here. Hengst et al. Is 1 minute, so it's very consistent. It's just a few ones. And what is interesting, well, for Lefar it's 4 hours, but it's not designed to run fast, actually. You have only, well, let's say 18 minutes on this computer, or similar one, and on a one with 20 cores, 9 minutes. So you can see that it's very comparable to this one. This one are much faster, but if you assume that you need some training before, well, you need to take that into account. So you can run on, let's say, something like 75,000 objects, the code very fast. One caveat here is that data is very small. That UGRIZ, so let's say something similar to SDSS, and Euclid 4 bands. What does it mean? It means that you don't need to assume any dust emission. I assume no AGN at all. So the modeling part is quite simple and fast. And everything was run on this sample. So it compared quite well. But remember that this was for photometric redshifts. And again, CIGALE is not designed for photometric redshifts. It's for physical modeling. And here, you can get the same type of thing. So Euclid with JWST, Le Phare, Prospector, and CIGALE, with assuming 6 parameters. The fraction of outlier, you see, is very, very good in this case for the 6 parameters. And the sigma and MAD is also very good. The training, again, none. The number of objects the same, models the same. But here you get 3 minutes on my computer here and 2 minutes on one with 20 cores. It was like this before, so this is very fast, of course. And, well, I don't know for Le Phare, but for Prospector, I feel this is quite strange, but I didn't check more. In these papers, I assume 3,000 cores, supercomputing system, with non-parametric SFH, and it took 24 hours. So, well, I just give you the numbers. I didn't check more than that, but it seems to be a lot. Well, this was done on a smaller number of objects. So I wanted to explore what we could get if you go to 1 million objects. So I don't have any other comparison, but I did the same type of values, so except that I have 1 million objects, same number of models, and this is the time that you get. For stellar mass, SFR, and 3 other parameters, data saturation, I don't remember exactly, you get this type of 20 minutes time. If you want only redshift, it takes 3 hours, which is, again, the same thing. If you want to estimate redshifts, you need to have very good sampling and many, many, many redshifts, so the code gets low in time. And, well, of course, it works quite fast. And you can see the result here. That's the SFR in, SFR out for the 75,000 objects, sorry, here. And you see that, well, of course, you go to very faint SFR. But if you keep in this region for the stellar mass and for SFR, you get quite nice, especially above, let's say, 10 in SFR, quite nice comparison. And its stellar mass, it's even better. If you do the same thing on 1 million objects, again, stellar mass and M star, well, that doesn't change the result. You get more population here, but still, you get a very good comparison for all of them. And this is the redshift that you get from Cosmos. This is the redshift that you get from CIGALE. And you see that for these 1 million objects, without prior information on the redshift, you get a very good agreement here, down from 0.78 to redshift 3, which was the catalog I used. So you get this type of results very fast. So if you hear about people telling this type of things, well, maybe you need to be careful. Of course, machine learning will improve and improve, and at the end, we'll certainly lose. But right now, depending on the approach that you use, it's not that clear. Now, if you want to practice, you can go to Patrice's workshop. I will be there as well to help him on Thursday. And that will be, well, unless you use what I said before, that will be on the photometric ACD code. But it's exactly the same process. Well, there are a few differences, but minor differences if you want to use the spectroscopic data as well. This was the universe from the beginning to the end. The end is now. And the future is yours. You can use it and work. And just now, we'll focus on the end of the presentation. Thank you.
Just going to turn the lights on.
Sure.
Other questions, please? Yeah, go ahead.
So when doing the spectrophotometric fitting, the spectra suffers from aperture losses, unlike the photometric part. How does CIGALE handle that, or do you need it handled before doing the fitting?
Well, there are different types. OK, let me go down. Well, I don't know where the mouse is. Oh, yeah. Well, I do that here. As I mentioned, well, you have different types of losses. You can have them because of the microshutters themselves, because of the aperture, etc. So we assume that the pipeline took care of the basic one. Of course, it could be improved, especially the background. But what we do into CIGALE is using the slit loss itself, because you have the microshutters that have some type of aperture. Photometry normally could be on the entire galaxy integrated. And so the process here try to normalize, if you wish, the spectroscopy to the photometry. So you can do it without any normalization, because you don't have photometric data, because you don't trust the photometric data, because it's not on the same part of the object. And then, as I said before, the type of correction that you apply depends on the quality of the photometric data and the spectroscopic data. We assume it's polynomial. But polynomial is not the entire answer. It can be 0 or degree 0, degree 1. So 0 is just constant, degree 1 a slope, or even degree 2, which is something varying. But we assume the degree of the second order polynomial is not too large as well, because you don't expect something like this. And so the code, CIGALE, tests what is the statistical relevance of each of the corrections, and assume which is the most significant. If we don't trust something because the test is not valid, we move to a lower degree, and then finally to the just constant normalization. So the code does it all by itself. You don't have to process. And then you can check at the end, of course, that it's valid. We also, because we have some, at the end, we were not sure of the quality of the data. You see there are a lot of errors. So we cut here to, if the band is too large, we don't use it. So we took care of this, and well, most of the time it works very well. Let me show you another one. Yeah, here. No. Yeah. If I try to enlarge.
Just a quick follow-up. If
Yeah,
I measure
I can't.
the aperture losses myself, can I provide that to CIGALE and
Yeah.
skip? Okay.
Yeah, no, you don't provide it to CIGALE. You do the correction before, and then you assume no correction into CIGALE.
Excellent.
And then it works. Yeah, what I wanted to say is that you see the spectrum is going up here and here, but with very large uncertainty. So this is excluded from the fit. In this case, we can check, because we have the MIRI 7 micron data point, that it would be a mistake to go up here. It needs to go here.
May I ask, should CIGALE fit V-shift SED, especially for those sources which is called little red dots?
Yeah, we have, well, actually, my PhD student is working in sample. I don't know if you know the Capers program. So we have many spectra, and we have identified by using SED fitting like this on the spectra that we have different, well, the traditional V-shape of the little red dots. So we can fit that. But right now, the assumption on the AGN is only on the continuum, which is enough, I mean, to get the shape. But if we want to confirm that they are actually AGN or not, we need to wait for the AGN emission lines that will come soon. But the continuum, it's OK. We can assume models for the AGN emission and detect and estimate the physical parameters that would be in agreement with an AGN assumption. So this is doable. Yeah.
I have many, if I may. So I saw this in your slides, but I missed the details. How does the IGM, how can the IGM be included in this procedure?
Well, the IGM is a specific modules. We had tried different values, but basically it's statistical, but we assume the absorption related to NOEMA model, which is well, a bit old, but still valid. And so we apply some absorption in the extreme UV to take off this IgM absorption. So it's in the process, it's done at the end when we do the redshifting, because we need the redshift, of course, but it's consistent with what we expect for statistically from the AGN absorption.
So I have a little question. Could you go to the page of 51? The slides. Could you go to the page of 51?
Yeah. Oh, it's above. Yeah, right. Oops. That one? 51. Oh, sorry. Good idea to 1. Oops. Too low. Yeah.
May I ask what is the second generation of true? Is the second
No, that's again the same mistake that here. It's 3.2. It's not 2.2.
just probably
Yeah. Except that you get lower stellar mass. Yeah, sorry. Very fast. Well, if you use the code, you will see it immediately.
Has CIGALE already been used on the stack spectra?
You can use it on anything.
And does it improve?
Yes, for the work I've been doing, I stack the object with very low dust attenuation. There are 49 of them. I stack everything. The signal to noise is improved, so the result is improved, depending on what. Basically, what you need when you use the spectra version of CIGALE, you need to provide CIGALE with the dispersion law as function of wavelengths. So if it's NIRSpec, you just pick the one that is available on the website. If you use a ground-based telescope like Mosaic or whatever, you provide this one. And if you have just something flat, you provide something flat. So it works. I tested on VMOS data only, not on other one, but it should work normally on anything.
Anybody else? You can have one more if you want.
No, you're the only one.
Okay. Okay. What if my spectra does not have a continuum? Would you still suggest that we use the spectrophotometric feed, or maybe it would be better to create like pseudo narrowband photometry by emission lines?
Yes. Well, you can have different reasons why you don't have any continuum. Let me check. I don't have any here, but well, sometimes you probably notice on NIRSpec data you have a hole here, for instance, and you don't have any data. So you just have this part of this part. If you have this photometric data, you can fill in inside the hole, and that allows you to compute the complete continuum. If for other reasons you don't have any continuum, but you just have the line, well, the normalization will be low, and this will appear at the very bottom, and that's it. You will just fit the lines.
Okay, yeah, basically I just have an extreme emission line galaxy, still no continuum.
Yeah, you can provide, you don't have any continuum photometric one? No, nothing? Yeah, okay, anyway. In the SED fitting, you can provide observed data. So if you have emission line, that works. If you want to assume SFR, luminosity, anything, you can also provide that as a constraint for the fit. So, but just line. Of course, the fit will not be excellent because you have less constraint, but you will have something.
Yeah. Can I add? You correct me if I'm wrong, but sometimes there's information and you don't think there's anything there, but there might be a low signal.
Yeah.
So actually fitting all the data, you shouldn't just cut out just the emission lines. If you fit everything, there could be a low continuum there, right? That that would be my feeling.
Yeah, yeah, sure. But actually, it needs to be consistent with everything. The continuum, the line, and everything else you provide as inputs. So even if it's slow, that's an information. That means that you don't have a strong continuum, at least.
Yeah.
So yes.
And yeah, also, if you have more questions, then you can.
Yeah, I'll be here.
Just,